In 2025, I spent 1,267 hours and 43 minutes just coding. I thought it'd be cool to review what I actually did this year and reflect on how things went. About 55.3% of that time was spent just on game development, 33.6% was spent on my job, 7.49% of that time was spent studying stuff related to programming, and about 3.49% of that time was spent studying maths. The reason that game development is so much higher than everything else is because I don't take any days off. I don't take any holidays, and basically that's all I've done all year. I work on game development before and after work, and my job doesn't always consist of just programming, which is the only thing I measured this year. So why do I time myself when I code? Well, it's systems versus goals. Let's just say, for example, you have a goal in mind to fix a bug. You could set this as a goal of something that you want to achieve today, but it's possible that you solve the bug in 20 minutes. And then what do you do next? The other alternative is you spend all day trying to solve this bug and you feel like you've made no progress. If you focus on how much time you're actually doing the task, then it doesn't matter if you solve it in 20 minutes, you still have all the time to put in. And it doesn't really matter if you don't solve the bug at the end of the day either. All that matters is you put in the time. I make sure that when I time myself, everything is deliberate. So I can't just sit there and listen to a podcast for 3 hours and call that work, because I'd be passively consuming something rather than being deliberate. If I'm reading a book, for example, on programming, that counts, because the intention here is to get better. It's all about the intent behind the action that makes it count. Because obviously you get better as a programmer if you put in the time. I want to be honest about this or I won't improve. Like, I don't want to be the guy who says they put in 40 hours a day of practice and makes no progress in anything. So let's get into it. What happened in 2025? So the first thing I managed to achieve on the 8th of January was to get compute and graphics to work concurrently on the GPU at the same time. This means I could do generic compute work and render at the same time. In this cloth demo, for example, I'm actually doing the physics work in a compute shader. I also started to use at this time indirect draw calls, which are pretty interesting because they take in a command buffer, and then based on some factor you set up in the shader, the GPU then generates its own draw calls. The whole point of doing both of these things is to reduce GPU and CPU synchronization costs and graphics driver overhead. If you want full details on this, you can check out my video I posted on the 17th of January. On the 3rd of February, I started to work on animation. This is something I actually never got working this year. I'll come back to this and explain why I never got this working in the end. The 21st of February is the first commit where I can see in my GitHub history where I started to work on mesh shading. The only reason I started to work on mesh shading was because it was chapter 6 in the book that I was reading, Mastering Graphics Programming with Vulkan. Working on mesh shading this early in the game engine's development would prove to be a mistake. This would be one of the reasons, despite putting in over 1,000 hours of work, there weren't many features that were added to the game engine. So this began my mesh shading arc for the whole year, which only stopped on September the 18th. I began working on mesh shading with the GTX 1070 graphics card. This graphics card doesn't even support mesh shading. So I spent $643, or £479, on an NVIDIA 4070 RTX graphics card. This was all so I could use this new graphics technique, which I eventually had to drop, because I never quite got it working. The first warning sign that this wasn't actually a good idea was the fact that I had to upgrade my graphics card. My NVIDIA GTX 1070 graphics card is getting old, but it's still likely true in 2026 that a lot of gamers still don't have graphics cards that support mesh shading. Which would mean for the rest of the time that I'm trying to code mesh shading, I would also have to support an alternative code path for the people who don't have access to mesh shading, like I didn't. Well, why is this an issue? Simply put, I've just increased the complexity of the whole game engine. This is because every single graphics technique I use with mesh shading to increase the frame rate, I'll now have to implement a non-mesh shading equivalent that at least tries to replicate the techniques that mesh shading allows. What's funny about this, at the time, I had no idea, and I was extremely overconfident. So much so that I decided to host a game jam, announcing it on the 23rd of February, that would last for 3 weeks, starting on March the 1st, and ending on the 25th of March, with the whole idea from the 23rd of February to the 25th of March. I would finish and implement mesh shading and every single technique that goes along with that, implement an alternative code path to support non-mesh shading, add physics, gameplay, and make a playable demo by the end of the game jam to try and win against people who are using game engines. I did end up making something by the end of this game jam, but I wasn't really happy with it. This was the Lost Souls tech demo that I released to the public. If you want to know more about how this game jam went, I finally got around to making a video about the game jam, which I published on the 27th of June, which I'll link below with everything else. I remember at the end of this game jam I felt incredibly frustrated. I was starting to notice that I couldn't achieve what I wanted to achieve at my current level of ability, but I couldn't yet pin down what was actually the issue. As soon as I would start to deviate from books, tutorials, and other resources I was using to learn, I would get very stuck very quickly. And at the time I didn't know the resources that were available for mesh shading, and it was still relatively quite new, and still is. So the resources out there are quite thin in comparison to other things. So on April 1st I decided to take a break from game development, and I thought it would be a good idea to study maths. At the time I would have told you that my mathematical ability was holding me back when it comes to making games. So I spent 31 hours, 48 minutes, and 38 seconds studying maths in the month of April, and only 8 hours, 2 minutes, and 25 seconds trying to fix issues in that game jam project I made. I could have spent this time better, but it was useful to go over some elementary algebra, linear algebra, and a little bit of calculus. I started back up with game development on the 3rd of March to try and fix some bugs with the Lost Soul game, and finally get mesh shading working. This was still a huge struggle that lasted all the way to the 6th of June, which is when I stopped using the Mastering Graphics Programming with Vulkan book. I'd been using this book as a general guide to teach me what I needed to know to make a good game engine. The idea being that I would use it as a foundation and branch off into other resources and use my past game engines to hopefully make a better product. The problem with this book was that the mesh shading code just doesn't work. This isn't the fault of the authors of the book, because at the time they were working with Vulkan 1.2 and mesh shading was still extremely new, and it only worked on Nvidia cards, unlike today. So the Lunar G validation layers that I'd been using to debug things was more advanced and picking up errors that weren't picked up in the past, meaning that I was having to fix the book's errors and my errors that I was making at the same time, making things even harder than they had to be. That's when I found out about Arseny Kapoulkine, an incredible graphics programmer who's made a YouTube series on mesh shading, where he implements mesh shading from first principles. I'd actually been using one of his libraries already without realizing it. So going forward from the 6th of June, I decided to follow his YouTube series about mesh shading. I would implement exactly the same renderer step by step, just to learn how to do it properly. I found this YouTube series a lot more useful, as each video corrected mistakes as time went on. Funnily enough, this YouTube series is actually referenced in the book itself. Anyway, I'll link my side project and anything to do with Arseny Kapoulkine below. I would highly recommend going through the YouTube series if you want to learn about mesh shading yourself. So on the 29th of June, I actually got mesh shading working for all static geometry, with plenty of help from Arseny Kapoulkine and his mesh optimizer library. Now I've finally got it working, let's talk about what mesh shading is. It's a new type of shading that replaces the pre-rasterization stages of the graphics pipeline into two shaders. These are the task shader and its fixed function counterpart, and the mesh shader. The mesh shader feeds data directly into the rasterizer. This is different than the traditional graphics pipeline, which typically has the input assembly vertex shader, control tessellation shader, the fixed function tessellator, the tessellation evaluation shader, the geometry shader, and then the rasterizer. As this has grown organically over the years, a few problems have arisen. The tessellation shaders are often quite niche and not always used, and the geometry shader, although extremely powerful, allowing you to generate geometry on the GPU, which can be used for all sorts of things, it's just not fast enough to be useful, as the shader model of the hardware doesn't match the GPU very well. Yes, the tessellation shaders and the geometry shader are completely optional while using the traditional graphics pipeline. That doesn't take away from the fact that things are getting quite bloated. This is what mesh shading is trying to solve. It's trying to simplify the graphics pipeline while giving graphics programmers more flexibility when it comes to writing graphics algorithms. While the execution model of the task shader and the mesh shader are very close to compute shaders, meaning it matches modern GPU hardware extremely well, allowing for good performance when using mesh shading. This technology was invented by NVIDIA and released to the public in 2019. The first graphics cards to support mesh shading were the NVIDIA 16 series GTX graphics cards on the Turing microarchitecture. Later in 2020, AMD started to support mesh shaders on the Radeon RX 6000 series on the RDNA2 microarchitecture. And on September the 1st, 2022, Khronos, the owners of OpenGL and inventors of Vulkan, announced the general extension for mesh shading. And in the same year, Intel's hardware started to support mesh shading. When using mesh shading, it's recommended you try to use meshlets. Meshlets are just tiny pieces of a mesh. These are a new primitive that work under mesh shading. The meshlets themselves can be made up of any number of triangles. However, when it comes to the size of meshlets, different vendors like AMD and NVIDIA have different recommendations for the size of the meshlets. So I decided to generate the meshlets in accordance to the NVIDIA recommendations, which is having 64 vertices and 126 triangles. What's cool about meshlets is the indices are actually stored in 1 byte. I'm using the Mesh Optimizer library to generate the meshlets on the CPU. So when it comes to culling, I wrote 3 different algorithms. 1. Meshlet backface culling. 2. Culling of those meshlets against the view frustum. And 3. Occlusion culling, which is done against meshlets and meshes. So this is an exclusive to mesh shading. I also do a quick view frustum cull, just because it's really cheap. So for the mesh shading flow, we first occlude the meshes. The mesh shading then occludes things further with meshlets. So let's talk how we occluded the meshes in the compute shader first. We are doing occlusion culling as part of the mesh occlusion early pass and the mesh occlusion late pass. We are building the depth pyramid in the depth pyramid pass, and as part of this technique, we have the gbuffer early pass and the gbuffer late pass. The algorithm that I used involves rendering the models first, and then checking if one is behind another, based on the depth value. If one object is in front of another, the depth value of the one behind it is greater than the closer one. We could just simply look at the middle of an object and sample the depth buffer there and see if it's behind another. The problem with that naive approach is that some objects are only partially covered, meaning that it would be occluded, even though it does need to be rendered still. So before we get into the algorithm and the approach I've taken, like I mentioned earlier, it's important to note that we're using indirect draw calls for mesh shading, which is a special type of draw call that takes in a draw command buffer, and then the GPU can generate the draw calls based on that draw commands buffer. This technique is known as GPU-driven rendering, because the GPU itself is telling the GPU what to draw via these command buffers. So the method I use for occlusion culling uses the meshes themselves as occluders, meaning that we're not using any special occlusion geometry. So no occlusion queries will be needed. There is one big drawback with this though. We are in a catch-22-like situation. We need to render the meshes for the depth buffer to be useful. But the whole point of this is to occlude the meshes themselves, meaning we have to run this compute shader twice. The first step is to use the previous frame's depth buffer. We check if things are being occluded, then remove them. The problem here is we might have some false negatives, meaning that we've occluded things that we're supposed to be able to see. So let's break down how this algorithm works in our compute shader. So the first thing we need to do is build a depth pyramid. This takes our depth buffer, uses it as a texture, and downsamples it over and over again. When we downsample, rather than taking the average of each pixel, we actually take the maximum value and save that to a texture. This effectively creates a depth texture with multiple levels of detail. Each level of detail getting lower in resolution as it contains a 2x2 grid of depth pixels that get larger and larger. This is what's known as a depth pyramid. You can see what this looks like if I bring up my side project. As you can see, we're going up and down the depth pyramid as I keep pressing keys. This shader that we looked at just creates the depth pyramid. We now need to use it So let's move over to the culling compute shader. First we get a bounding sphere from a shader buffer object that we've sent up to the shader. Next we get the instance of the model this draw call corresponds to, and with that we can very quickly do a viewForUstem call to check if it's behind the camera, using the viewForUstem planes we've uploaded to the shader. This for loop goes through each plane, and the condition inside the for loop tells us if the sphere is in front or behind the plane. The next step is to take our model and see at what point in the depth pyramid is it completely covered by a grid of 2x2 depth pixels, meaning that we need to find the appropriate level of detail for our depth pyramid depending on our model's size and location. The problem here is we only have a bounding sphere of the model to work with, rather than a 2D texture. If we did have a texture, we could use the texture LOD function. This would get the appropriate level of detail using the UV coordinates of the texture we pass in. So basically we need to turn that bounding sphere into a 2D texture. There's this paper out there that describes how to take a perspective projected 3D sphere and get 2D polyhedra bounds. This algorithm is super generic, as it even deals with spheres that are clipped by the camera's near plane. Fortunately, Arseny has actually already simplified this algorithm for us. We don't actually need to care if anything's clipped by the near plane, as we are going to be removing those models anyway. This is what the first if statement is trying to do. It checks to see if the sphere is behind the near plane. If it is, we reject this case and move on. And the second thing is we only need a 2D axis-aligned bounding box. Okay, let's break this down. I've used a lot of terms just now. The perspective is pretty easy to understand. Things get smaller as they get further away. Pretty much all 3D games use perspective distortion to replicate perspective to the viewer. So what's perspective projected? That's just taking an object that's being transformed by perspective and projecting it onto something. You're already very familiar with this, because 2D games and 3D games are all projected onto a screen. So what we end up doing is projecting our sphere onto an XZ plane and a YZ plane and getting the maximum and minimum bounds of this projection. We then build up the axis-aligned bounding box with some of the diagonal values from our perspective matrix that comes from our camera. We can do this because our perspective matrix is symmetric. This method will break down if your perspective matrix isn't symmetric. Non-symmetric matrices are typically used in VR games. After we've done this, we have an axis-aligned bounding box that's warped by perspective. Then we take the axis-aligned bounding box and convert it to UV coordinates, with a minor offset of the Y coordinate. Now we have enough information to access the depth pyramid at the correct level of detail. Next we need to calculate the level. This will give us the correct level of detail to return a depth texture that covers the entire model. We do this by taking the logarithm of the maximum value of the height or width of the bounding box. Next we need to calculate the UV coordinates. This is so we don't return the whole depth texture. We're only interested in the part of the depth texture that's covering the model. So with the UV coordinates, the level, and the depth texture, we can now finally use the texture LOD function to get the depth value we're interested in. Next, we want to sample over the 2x2 grid of pixels at the appropriate depth level, using our axis-aligned bounding box and the level variable which tells us which level of detail we need to look at. Because there's 4 pixels, we need to do this 4 times and return the maximum value of whatever pixel has the highest depth value. After that, we figure out which direction we're facing, and depending if we're on the late or early pass, we use the previous perspective or the current frame's perspective, multiplied by a 4D vector that's constructed by the world bounding sphere plus the direction we worked out earlier, multiplied by the radius. With this final division, we actually get the depth of the model. And with the depth value we calculated earlier using the depth pyramid, if the depth sphere variable is behind the depth value, then we can say this whole thing is occluded. So what's this early and late pass thing about? Well, if you don't run this algorithm twice, we get false negatives, meaning that we have occluded things that should have been rendered. This is because the current frame is almost certainly updated from the previous frame, either through camera movement or something moving around in a game, meaning that we've occluded things that should be in this scene. The idea here is we use the draw command buffer itself to create a sorted list of the false negatives. Then in the late pass we go over this list, removing all the false negatives and positives of the current frame, and rebuild the depth pyramid of the current frame. We do this so we can repeat the process again. Finally, we can build up the command buffers that we're going to send to the mesh shading. The only difference here in this if statement is if a model has transparency or not. This is because in the fragment shader, for transparency, we need to test for alpha and transparency and all that kind of stuff. And finally, this if statement at the bottom is only used for the late pass to add false negatives back into the draw command buffer. It's important to point out when we're building the command buffers up, the first and last task are operating under the fact that we're going to use 32 threads per warp. When you're working with NVIDIA cards, it's recommended that you use 32 threads in their warps. But for AMD, it's 64. This code needs to be improved to be more general. It's not that AMD won't work at all, it'll just be slower because it recommends 64 instead of 32. You see, when you're using mesh shading, it's very important that you look at what the vendor recommends. This is because you can get quite a big speed up if you follow the vendor recommendations. And for those who are wondering, a warp is just a group of cores that can run threads in a highly parallel way because they're really close together. Okay, so let's talk about what the mesh shading is actually doing. One quick thing I should mention that all the talks and the tutorials I've read on mesh shading talk about is that you can get faster than a traditional pipeline using mesh shading, but it's hard to beat. You really have to follow what I said before about the vendor recommendations. The real advantage of mesh shading isn't the performance gains that you can potentially get, but the features you can have access to. Another thing to mention is the execution model of the mesh shaders are closer to compute shaders, which means you have to write algorithms differently than you would say on a vertex shader, for example. This means that unlike vertex shaders, you don't work with a particular type of primitive. You can upload generic data to these mesh shaders, meaning you can't use the import assembly to push vertices onto the shader. This has some drawbacks, but it has an upside too. This means that it's impossible with mesh shading to use a vertex buffer, meaning if you're already using a vertex buffer, you need to upload the vertices in a different way, potentially increasing the complexity of your code. The upside of this is you don't use the fixed function step, meaning that this import assembly, which can be a bottleneck, is removed from the process completely. So it's good to think about this with mesh shading as you're not pushing vertices like you are with a vertex shader, for example. It's more like you're just pulling the vertex data off the CPU with something like a descriptor set. I've uploaded the vertex attributes of the models with a shader storage buffer object, which is like a uniform buffer object, but it's perfect for storing arrays of data. I personally found this extremely difficult to get right. When you're uploading generic data to the GPU, it needs to be 16 byte aligned. This means if you get the padding wrong, you just upload junk data. As you can see in this example, everything's red, nothing makes sense, and it's really difficult to figure out exactly what is going wrong here. But this is a very typical issue that you'll get if you're uploading buffers to the GPU that aren't aligned. The index buffers now need to be very carefully matched up with the buffer that you're uploading to the shader. And because I wanted to save space, I also quantized the vertex attributes, meaning that everything was compressed, so it's hard to figure out exactly where I was going wrong. This is something I never got quite right. Because the code paths between the mesh shader and the non-mesh shader are so different, I introduced this really annoying bug, which you can see clearly if I switch between mesh shading and non-mesh shading. I believe something goes wrong when I reorder the vertices and indices for optimization, which I don't do in the non-mesh shading path. Anyway, so now we got the vertex attributes in the task shader. Let's talk through Meshlet backface culling, which is the first algorithm I got working. You see, with Meshlets, backface culling has to be handled explicitly. Culling is pretty straightforward when you're working with triangles. This is because it's very easy to figure out the normal vector of the triangle, which you can think of as a small arrow that's pointing forward with a length of 1, showing which way the triangle is facing. We can easily work out this normal by the triangle's winding. We can take a triangle and count the vertices clockwise or anti-clockwise. So if we take the indices of this triangle and count 1, 2, and 3, we can then use the vertices to figure out the normal vector. And if we count 1, 3, 2, we have the opposite direction, meaning that we have a different vector normal, which tells us that the triangle is facing the opposite direction. So now with meshlets, we need to figure out which way they're facing. Well, fortunately, there's a well-known way to do this. You take all the triangles and add all the normals together. This generates a cone. Typically, not all triangles are facing the same direction in a meshlet. The wider the cone, the more different the normals are of each triangle that makes up the meshlet. I'm using the Mesh Optimizer library to generate the cones with the meshlets, along with the bounding spheres, which I used in a different algorithm. Let's go into the Mesh Optimizer library and look at the struct with all the data in that we're going to pass up to the shader. These first 4 floats make up the bounding sphere of the meshlet. The cone axis tells us the direction of the cone, And the cone cutoff gives us the angle. This is the angle at the top of the cone. The other values down here are the cone axis and the cone cutoff values, meaning we can save bandwidth when passing things up to the shader. The only difference is we would have to decompress this on the shader. But the arithmetic is really quick, so this isn't an issue at all. I haven't used the cone apex here. It can be used for better culling, at the cost of a more expensive algorithm. The culling by itself is so good without the cone apex that it never made sense to use this algorithm. So let's decompress these quantized values. You can see it here in this multiplication, where I get the cone axis and the cone cutoff. And now we can use this data in the shader. Next we compute the cosine of the angle, and using the center of the bounding sphere, we can get the vector that faces towards the camera. Then I scale the cone cutoff by the distance between the camera and the center of the bounding sphere plus the radius of the bounding sphere. This calculation works out if the cone is facing towards or away from the camera. So if it returns false, we can cull it. Remember, this is all done in the task shader. This is important because the task shader generates instances of the mesh shader, meaning we can increase or decrease the amount of times the mesh shader is ran. So all the occlusion culling algorithms we're going to run are in the task shader. We're trying to reduce the amount of work the rasterizer and the fragment shader have to do by removing as many instances of the mesh shader as possible. You can of course generate more instances of the mesh shader if you need to, kind of like how the tessellation shaders used to work. I'm not currently using any techniques like that. I mentioned earlier when I was talking about generating the meshlets that I also generated bounding spheres for those meshlets. As you might expect, you can run the same culling algorithm on these meshlets that we did with meshes earlier. So the first thing I did, like before, I do a view frustum check by looping through all the view frustum planes. So this code here might look very familiar. There is one major difference though. We don't have to run this twice, because the culling work we did earlier in the compute shader solves that for us. There is a huge advantage culling per meshlet. We can cull geometry from large meshes. When we are culling per mesh in the compute shader, it's possible that you can have big models in the distance that don't get occluded. For example, this mountain in this demo. Even though the camera can't hardly see it, it's almost always drawn. Since we have bounding spheres around the meshlets, we can break things up and cull them individually. If I freeze the camera, you can see the result of this. Although I'm getting ahead of myself, we haven't looked at the mesh shader. Despite it being mandatory to use, if you're using mesh shading, there isn't much going on here. We are just transforming the data, as we would in the vertex shader, but using meshlets and operating in warps, so in this case 32 threads at a time, and then we just write out the indices and the triangles. Again, following vendor NVIDIA guidelines, I'm outputting 64 vertices and 124 primitives. According to NVIDIA, it should be 126. Outputting 124 primitives didn't seem to make any meaningful differences when it came to the output of the mesh shader. So that's all I wrote for the mesh shading GPU-driven pipeline. It's a huge topic that spans all sorts of techniques and effects. I hope it did a good job explaining how all this works. I'll provide some resources below in the description for those people who are interested in exploring this further. I did say earlier that writing mesh shading code was a mistake. This isn't strictly true. Programming graphics well is difficult. There's a lot of highly specialized knowledge. A lot had to change on the CPU and on the GPU, and I ran into so many bugs that it just dragged out. And a game developer friend of mine asked, am I making a game or a game engine? And I realized at this point that the mesh shading was getting out of hand. It was taking too long, and I hadn't made progress on any other front. I didn't have a 2D renderer for UI, I didn't have any type of physics for collision detection, or anything else a game would need to be playable. The other major issue I was having was all this mesh shading work only worked for static geometry. There was more work here needed to be done for animated models, as the cones and spheres that were generated with the meshlets needed to be big enough to support movement that would happen within the shader when it comes to animation. If I just ran these mesh shading algorithms naively, you would see holes in the model when the character animates. I'm aware now that I'd have to walk the hierarchy of animation and consider the maximum ranges of the skinned models when I'm generating the cones and the spheres. However, this is hard enough to get right when you don't even have animation working in the first place. So when I say mesh shading was a mistake, it was a mistake in the sense I didn't prioritize things correctly. I should have made more progress and then gone back to mesh shading. And then I could have spent the time moving to a fully GPU-driven renderer, using all the power that mesh shading provides. So, what else did I do this year? On the 9th of July, I paused work on mesh shading and removed the hand-rolled GLTF loader I had been using for a while, and moved to CGLTF. This is where I started to struggle with tech debt. It had always been there, but when I added the mesh shading, it got so much worse. The engine was supporting so many different code paths. When I was trying to remove the hand-rolled GLTF parser to support GLB files to improve load times, I had to rewrite a large part of the engine just to do that. After that, I tried to work on the model loader for a full month. I have a problem here that's extremely common for people making their own game engine. You have no artist to work with, so you end up pulling models and art from the internet. And every model I would use would have some kind of issue. It's not the libraries I was using, so CGLTF wasn't the issue. It's actually parsing the data that comes out of these libraries. Meaning sometimes I would get a model that uses a feature my engine doesn't support, causing issues I would have to fix. At one point I tried to implement compressed textures which I saw was being used in a model. But it turns out when I figured out what to do and wrote all the code in the shaders, CGLTF at the time didn't support this extension. That's just one example of what was happening at the time. On the 15th of August, I got the opportunity to be interviewed by one of my game developer friends, Kukatoo. He has a cool YouTube channel where he talks about all things game development related. So if you're interested, I'll leave it linked below. On the 18th of August, I finally parsed animation data from the GLTF files. This only really worked for very specific models, so I wouldn't say I got animation working. At this point, I really started to feel like an imposter and a fraud. Everything was going so poorly, and I thought at this point I would at least have something playable. Because I hadn't released anything recently, I felt like I was starting to let people down. So I thought at the time it would be a good idea to host a game jam, assuming that I needed to work harder and apply pressure on myself, and make a game as fast as possible. So I hosted a month-long game jam, starting on September the 1st, and I decided to call it quits on the 19th. Some cool prototypes and games came out of it, but for me I misdiagnosed the problem. I did need to work harder, and I still do. But making a game as fast as I possibly could was repeating mistakes that I already made. This is what was causing the tech debt in the first place. So starting from the 19th, I took a little break and decided to really figure out how to learn better. So on the 28th of September, I started to apply what I learned about learning and went back to the basics. I went back to the original Vulkan tutorial from 2016. In retrospect, this was a brilliant idea. I now go over the basics every day. I like to think about going over the basics like how fighters never stop working on their fundamentals. Just because I've done more advanced things like working with mesh shaders, this doesn't mean I should ever stop reviewing things, like how to create the swap chain for example. On the 16th of October, I started to write my new game engine, Void. At this point it was purely meant to be a small renderer that would pair with my studying. So every day I was either studying operating systems, Vulkan, or how to write more performant code. So after doing this for a couple of months, I realized I was improving by quite a lot. My feelings of being an imposter and a fraud started to wane. There was one drawback of this though. I really started to notice my mistakes from the past. So on the 10th of December, I decided to start developing the Void engine more seriously. This was going to be my new attempt of simplifying everything. One of the things I had learned about at the time was data-oriented design. And in doing so, I had watched this Mike Acton talk from 2014, where he said in his talk, one of the 3 programming truths are that hardware is the platform, not the software. With this in mind, I looked at my old engine. I really started to consider the decisions I'd made developing this engine. For example, in Vulkan, I was supporting a bindless and non-bindless code path. I hadn't considered the hardware I was targeting, so I thought it would be good to support both. But then I was curious and looked up the specifications of this old GPU that came out 14 years ago, the NVIDIA GTX 650 Ti Boost. That supported bindless textures and descriptors. Seeing that made it incredibly obvious I didn't need to support a non-bindless code path if I'm targeting desktop GPUs, because if a GPU of that age has that feature, then pretty much all GPUs have that feature. The other mistake I'd made in this engine was I was compiling GLSL code like I was using OpenGL. This is very slow because it has to access the disk twice, because I'm doing SPRV reflection on top of that. And you can see that happening in the Lost Souls demo. But this is only necessary if you have the requirement that other people are going to write shaders for your engine. For me, I didn't need this feature. I can just send you pre-compiled shaders, speeding up startup time. I also had way too many layers of abstraction. As my friend has always said, abstraction can solve any problem, except too many layers of abstraction. So these are the major reasons why I've started to work on a new game engine. Another thing I want to do is get this game engine natively running on Linux. The reason behind that is because I can slowly see that gamers are starting to use Linux more and more, and Microsoft is just being annoying with its refocus on AI and how it's handling Windows 10 and 11. My eventual goal is to get my game engine running natively on the Steam machine that Valve's created. Despite how things went with mesh shading this year, I do want to add mesh shading to the Void engine eventually, as I do believe mesh shading will eventually become the standard. So you could say, in a way, I'm back to square one again, but with a lot more experience. I'll eventually get back to where I was with all the nice features that I had, but hopefully with a nicer data-oriented design like Codebase, wayless lines of code, and very limited tech debt. To the people who are disappointed by the fact I'm basically starting again, I've made all my code open source. So hopefully that's something. And for those who are interested, at least you can see how not to do things. I'm definitely open to feedback when it comes to my code, but for now I won't be accepting any pull requests. Well, I hope you found this video at least a little bit interesting. Even though in 2025 I spent 1,267 hours coding, I want to do even more. I want to keep improving. So this year I have a goal to work even harder, regardless of circumstance. I just want to give a quick shout out to my small community, who have been helping me in my Discord and my live streams. Say hello if you can catch me live. I hope everyone's having a good 2026 so far, and everything's going well for you. Alright, thanks for watching. See you in the next one. Goodbye.